So for this learning module, I wanted to go over an additional example of computing force couple systems at a particular point in 3 dimensions. So here we have 3 forces acting on a plate, and we're asked to determine an equivalent force couple system at the origin. And in addition, since these 3 forces are parallel, we know that we'll be able to actually reduce this system of forces to just a single force acting on a point, and we want to find the location of that single equivalent force. So if you wanted to do the problem without doing any math, you could probably get pretty close to doing this one. Remember, if you want to determine the resultant force of a force couple system at any point, you just add all the forces. And since these are all in the z direction, you're just going to have 900 going down, 100 going up. That's going to mean 800 going down. So the resultant force is going to be minus 800 newtons at any point, including the origin. And if we were to want to compute move all 3 of those forces to the origin, we would just need to compute their moments about the origin, and that's going to be a pretty simplistic calculation because for the majority of these, you have perpendicular distances. You'll notice that the way the book does this, though, is rather than working it in a scalar-based approach, they actually use a vector-based approach just to make the bookkeeping easier, and you'll see why that is on the next slide. So this first line is just saying that if you add those 3 forces, you get minus 800 newtons in the negative z direction, or minus 800 k hat. When you move all those forces to the origin, you need to account for the rotation that they induced when they were at their original point. So what's going on with this first calculation? Let's look. That is the 100 Newton force, and notice that that is in the positive z or k hat direction. In order to compute the moment of that force about the origin, I just need a position vector from the origin out to any point along the line of action of that force. So the easiest one to use is just 3i hat cross 100 k hat. Now, the magnitude of that is easy, right? 3 times 100 is just 300. How do you easily get I hat cross k hat? That's where it's going to come back to remembering that rule of thumb for computing the cross products along a unit circle. So it's good to have that handy when you're working your test or working your homework. Remember, if it's I, J, K, and you move in the counterclockwise direction, that's positive. So if you add I cross K, that's moving in the positive clockwise direction. That would actually be negative. So that's where that negative is coming from. So when you're computing each of these products, you not only have to consider the product of the actual magnitudes, but also what happens when you take the cross products of the vector. What is going on here? Well, that is the 500 Newton force in the downward direction, which is located here. It is the negative just indicates that it's a negative z. What would be the position vector from the origin to the point of application of that force? Well, in y, we would go out 4 units, so that's going to have 4j. And in x, we would go out 4 units, so it would have 4i. And that's where the 4i plus 4j is coming from. When we take a cross product across a sum of 2 vectors, remember we talked about earlier in this chapter that the cross product distributes over addition. So we just would take the cross product of the first for I hat cross minus 500 k hat. That's going to be minus 2,000 I hat cross k hat. We said previously that I hat cross j hat is minus I hat cross k hat. Easy, do as I say, not as I'm writing. I hat cross k hat is minus j hat. The main reason I'm bringing that up is if you notice that the minus seems to go away. Remember, we talked about that a little earlier in this lecture. It can if in the case of 4 times minus 500, you have a negative, but in I hat cross k hat, you have minus j hat, and the 2 minuses would cancel. So just be careful with your bookkeeping here. Notice that this is the only force that, in terms of the position vector from the origin, has both an x and y component. So the rotation that it induces is going to be have 2 components associated with it. Since any moment is a vector, you can simplify it by just combining the components along the same unit vectors, combine the j hat terms, combine the I hat terms, and we get an expression for the rotation that these 3 forces induce about the origin. Now, let's actually see if that physically makes sense. When you talk about the tendency to induce a rotation about the x-axis, well, what would contribute to that? Well, this 400 Newton force, it's at a perpendicular distance of 4 meters, so it's going to have 1,600 Newton meters of rotation. If you imagine holding that plate along the x-axis, it's going to tend to rotate in the clockwise direction about the x-axis. So that would be minus 1,600 Newton meters. That's where that quantity is coming from. What about this 500 Newton force? Well, it's the same idea, and it would contribute minus 2,000 Newton meters. Those are combining to give you the aggregate rotation about the x-axis of minus 3,600 Newton meters. And about the y-axis, again, just pin it there. Notice that that is going to rotate it clockwise about the y-axis, and that would be 3 times 100. So since it's clockwise, it's negative. That's the minus 300 term. This 500 Newton force is a counterclockwise rotation, and it would just be 500 times 4, or positive 2,000. So combine all those together, and we find that the moment that we've computed does physically make sense. So if we want to determine where you would put a single force along that plate to induce the same type of rotation, well, if you think about it, in order to determine the location out and y of this force, what you need to do is pick a location such that the perpendicular distance times the resultant force in the y direction, which is 800, would give you that 3,600. So just doing your math there very easily, what you find is that out in y, you take that 3,600 in the negative, divide by negative 800, and you get 4.5. But what that's basically saying is if you know that the resultant force has to be 800 newtons down, you have to move away from the x-axis by 4.5 meters in order to induce that 3,600 newton meters of rotation. How far do you have to move away from the y-axis, which actually gives you your x location? So the main point I'm trying to make here is just notice that in order to determine the x location gives you how far you move away from y. So it's actually related to the moment about the y-axis, not the moment about the x-axis. So that's why the coordinates appear to change on you to some extent. But that's all that's going on here. So it's the same case for 2D as 1D. What they're trying to show you is for 3D as 2D. And the point they're trying to make here is when you move to 3 dimensions, oftentimes it's easier to just use vector techniques, even if the underlying vector mathematics is simple, just to keep your bookkeeping straight. You're less likely to make sign mistakes as long as you have your IJK unit vector easily in front of you.